This colorful mess of redstone wires, lamps, and levers is a fully functioning redstone computer. Literally one of the oldest things that you could ever make with redstone, with players all the way back in 2011 building CPUs with nothing more than the dust and torches that were available at the time. But wait, the more I fly around this, the more you might notice some weird things. Like, where are those redstone torches I was just talking about? Okay, well, computers nowadays use a lot of comparators, but I don't see any of those either. Wait, is that a redstone clock? Hold on, why are there hundreds of redstone clocks running throughout the whole thing? And why are there red mushroom blocks? What you're looking at is possibly the single worst redstone computer ever made. It's slow, inefficient, laggy, and yet no one has ever made a CPU quite like this before. It's the result of an arbitrary redstone challenge taken to an extreme it was never supposed to go near. A redstone build so stupid, I decided to give it an equally stupid name. This is the story of my first redstone computer. This is the story of Slow Rocks. The day is March 11th, 2019, where a redstoner named Cass would upload this redstone challenge. The rules were simple. Make a redstone torch only using repeaters and redstone dust. If you didn't know, redstone torches act like an inverter. If you power it, it turns off. If you leave it alone, it stays on. So how the heck do we do that with repeaters? All these things do is carry a redstone signal, have this locking mechanism, and I guess you can make a redstone clock out of them? And well, that is literally all you need. Behold, my solution made a day later with lots of redstone jankiness that I will now explain. The circuit has three main parts: the pulse generator, the redstone clock, and the clock lock. The generator will send a pulse through this repeater only when the input turns off, using the power of locking repeaters. That pulse then goes into a redstone clock, which can keep the output on with perfectly timed alternating redstone signals. And lastly, the clock lock. To stop the clock, we need to lock one of these repeaters while it's turned off. This yellow circuit basically only lets the input signal go through while this repeater is off. Now, this version didn't last long and would be compacted just a few hours later, but 2019 14-year-old CraftyMasterman wasn't done yet. If you could replicate a redstone torch, then you have a NOT gate, and if you have a NOT gate, you can make more logic gates, and with more logic gates, you can start adding in binary, and that's about where 2019 14-year-old CraftyMasterman stopped, and this idea would be shelved for over 6 years. So why am I here again, revisiting this 6-year-old redstone challenge? Well, I don't know if my long-form viewers know, but I post a lot of shorts now on various redstone challenges. And as I was looking through my synergy plot for more challenges to farm subscribers from, I saw these guys again and thought, this could be a good short and get me many subscribers. So I redesigned my OR gate, NOT gate, AND gate, XOR gate, and half adder, but by the time I got this far, I thought, wait, at this point I made enough content for a full-length video. And if I can make a binary adder, could I make an entire CPU with just repeaters? And still farm a lot of subscribers. But before we continue on this terrible, stupid rabbit hole, let's quickly go over the basic logic gates. This is our brand new NOT gate now in a 4x4 footprint. The pulse generator now doubles as the redstone clock, and these two repeaters are the locking mechanism. Using 3 NOT gates arranged like this, we can make an AND gate, and arranging them like this, we can get an XOR gate. And finally, combining them, we can make a half adder, which takes 2 inputs and outputs sum if one is activated, and carry if both are activated. Another useful circuit we will use later on is this, a series of 2 NOT gates back to back. This functions very similarly to a comparator on subtract mode, where you can completely disable it by powering the side. Using 2 NOT gates, if we power the second one constantly, it will always stay off, essentially disabling the circuit. These things will be the building blocks of our CPU. But I've never built a CPU, so where do we even begin?
Just made an entire series about how to make a redstone computer from scratch, starting from the very beginning by designing.
Well, that's convenient. This is MatBatWing, certified nerd and computational redstone extraordinaire, and we're gonna use this video to make our CPU. And if you ever want to make your own redstone computer, I highly recommend watching this video. If it can help me build a computer with these really stupid restrictions, then it can definitely help you make one, well, normally. In Matt's series, this is the final CPU he makes in diagram form. It's got 7 main circuits, but for our CPU, so I don't go insane, I am dropping that to 5. The first thing we need is the ALU, which is the part of the CPU that actually does all the arithmetic and logic operations like AND, XOR, NOR, and addition. Using 2 of these half adders we made, we can make a full adder, and then chaining 8 of these together, we can get an 8-bit adder. Now surprisingly, this is most of the ALU circuitry done, since we can actually modify different parts of the adder to make it perform different operations. For example, if we want to do subtraction, we just invert one of the inputs using an XOR gate and add 1 with the carry in. What about inverting an input and turning all the carries on? Well, now it behaves like an XOR gate. In total, there are only 5 things we need to modify in this adder to get all the operations we need. Inverting input A, inverting input B, carry in, which is basically adding 1, flood carry, which turns on every single carry signal, and what Matt calls the XOR to OR. And now here is hurdle number 1 in a long track of hurdles. As of right now, following this video was pretty smooth sailing. Every time there's a logic gate, I could just paste in one of these pre-built circuits. What this XOR to OR control does is take the XOR gate in the first half adder and override it to act like an OR gate. Now, Matt can easily do this by powering this torch, but remember, our XOR gate is based off this 3-torch design, and the only way to turn this into an OR gate is to completely cut off one of these redstone lines. Now, we can do this with a locked repeater, but what if the signal is on? Then our XOR to OR control gets locked and stays on, which we don't want. So this is the janky solution. First, we make a completely new control line that forces both input A and B to be off. Second, we activate the XOR to OR after enough delay so everything turns off, and finally let the inputs back through. And here is all that thrown together in this red blob. Oh my god, what have I gotten myself into? Now before we continue this nightmare of a project, let me tell you about something smarter you can do right now. Did you know that you could do redstone in real life? It's called programming. And just like how I'm using Matt's tutorial to learn about redstone computers, you can learn how to do backend development with today's sponsor, boot.dev, baby, we're back. Boot.dev is the smartest way to learn how to code. With fun. I love fun. There are so many courses you can take, from Python to JavaScript to Go, and every course has you coding a lot to make sure you learn everything you need to know. At the end of this video, I actually had to make a Python script to generate some programs, and well, I was pretty rusty at it. So I did a bit of brushing up on their Python course. Okay, let's fix our first bug. The combat system isn't working, and there's a plus sign here. I think this should be a minus sign. Let's run it, and there we go. We get our XP, and we can move on to the next thing. So go to boot.dev and try out the courses for free, and then use my code CraftyMasterman to get 25% off your entire first year if you choose the annual plan. So where were we? Right, the janky ALU. Turning on the right combination of control bits can give different operations on the ALU, but it would be much better if we had a single input activate that combination. Introducing circuit number 2, the control unit. Now in Matt's diagram, there's actually no box for this, but instead it's represented by all of these blue arrows. The control unit is a big circuit that takes a 4-bit input and translates that to activating different parts of the CPU to execute that instruction. This circuit will be constantly updated as we add more and more to the CPU, so for now, let's add all the ALU operations: add, sub, and NOR, and XOR. We also have this separate yellow circuit that shifts all the bits to the right. So let's add a right shift to the table as well. So great, we have a working ALU, but right now we have to put in all the numbers manually, and we want to do that automatically. Otherwise, doing a bunch of operations back to back will suck. So introducing circuit number 3. This is a giant tower of 15 8-bit registers with a data input, writing, and dual read. Now, altogether, this seems really complicated, but we can take 1 bit out of one of the registers and break it down. This is where the data gets put in, and it's stuck behind these locked repeaters, and if we want to write to this register, we have to briefly unlock these repeaters to let the signal through. The signal then gets put into this pair of double NOT gates, which, if you remember from earlier, acts like our disabled comparator. Depending on which line we turn off, we can read from either register 1 or 2. If we want to put an 8-bit number, we just add 7 more, and if we want more registers to write to, we just stack it up 14 times. These orange decoders take in a 4-bit number and will output whatever is in that register into the ALU, and because we have dual read, we can read 2 registers at the same time. Now, writing oh boy, hurdle number 2, writing. Remember how I said we need to briefly unlock these repeaters to write to the registers? Turns out that is really freaking hard when you're only given repeaters to work with. So here is the epic janky solution. This is a latch built with 2 NOT gates. The reason we have a latch is because we need a pulse long enough to go through these slow NOT gates to activate one and only one of the addresses, because we don't want to accidentally write to a bunch of them at the same time. Now here's the thing, these NOT gates are really freaking slow, so we need a second slightly shorter pulse extender going into the latch just so it can activate properly and not become a redstone clock. So we have a pulse extender going into a longer pulse extender. Anyways, I'll save you the headache, the right function now works, thank God. Lucky for me, the next component ended up being one of the easiest of the CPU. So let's introduce circuit number 4, the instruction memory. Yay! This is the circuit that actually stores our program, and I won't bore you with how I made it because, like I said, this one is pretty easy. Remember those decoders we made for the registers? Well, instead of making one with a 4-bit input, we make one with an 8-bit input with a total of 256 addresses. 0 starts here and goes to the right, and then once it reaches the end, it goes to the line above. The complicated part is connecting the output of this absolute cube to the right parts of the CPU and adding the instructions to the control unit. Now that we have registers, the next 2 operations that were added were load and add immediate, which use the last 8 bits of the instructions slightly differently to the ALU operations. For the ALU, these bits are the registers that get used as the input of the operation, and this green text is the register it stores that result in. For these immediate operations, these bits are used to tell the CPU which register we want to store the immediate value to, and the next 8 are the number we store. This section consisted of me building more of these double NOT gates in different parts of the computer, spaghetti wiring the instruction memory outputs to wherever Matt told me to, and still screwing that up and getting one of my circuits backwards. But after some time, we finally got load immediate and add immediate working epically. We can finally move on to the final circuit, the program counter. This is what keeps track of what line in the program we're in. It will also be responsible for our last 2 operations, jumping and branching. Jumping is an instruction that lets us skip to any specified line of our program, and branching is basically jumping but with a condition. For example, only jump to line 4 if the output of the ALU is 0. Our ALU already has 2 flags, carry out, aka the overflow, and 0. We can also invert them to have 4 total flags, 0, not 0, carry out, and not carry out. And this was the final and probably tallest hurdle. Guys, it is really damn hard to make a counter with just repeaters for some reason. At first I wanted to see if I could replicate this counter design from Matt's video, and I came really close, only for it to not work because this thing is stupid and inconsistent. A whole day was spent trying to make my program counter, well, a counter, until I saw the second possible solution. Make it a small adder. Now this was mildly terrifying because this is how big the adder in our ALU is. This thing could probably be its own continent and couldn't possibly fit in this tiny space we have for the program counter. Okay, well now it fits in the tiny space we have for a program counter. Okay, so turns out it wasn't that bad, and all I did was stack each bit on top of each other rather than side by side, and would you look at that, we get our compact little tower. So if we want to go to the next instruction, all we need to do is add 1 to the program counter.
But Crafty, that's only adding to the program counter. How are we gonna do jumping?
Well, more of these double NOT gates, of course. Using 2 of these, we can either choose the output of the program counter or the instruction memory to feed into the program counter input. And now that our counter can jump, we can attach our flagging system from earlier to it as well to add branching. And finally, let's add a clock and a halting instruction so our programs can stop themselves. And with all this, our CPU is now Turing complete, so we can log out for the day and... wait. Crap, we can't log out with over 1,000 redstone clocks running, can we? Well, the answer to this problem has been present throughout the whole video. All I need to do is replace all these mushroom blocks with glass, and then redstone blocks, and then back to mushrooms, and boom, my computer has now exploded from all the lag, and every clock is now reset and ready to go. So with our CPU ready, how do we actually program it? Well, the instruction memory has space for 256 instructions, with slot 0 reserved for a no-op. Each instruction is 16 bits long, with the first 4 being used to tell the CPU what instruction to execute. For the ALU operations, these bits are used to tell which registers to use as inputs, and these tell the ALU which register to write the result into. For the load and add immediate, the last 8 bits are the immediate value, and these 4 bits are the register that the value would be loaded/added to. For jumping, the last 8 bits are the address it gets jumped to, and branching is very similar, with the only difference being these extra 2 bits that are used to specify the jumping condition. So let's put in a program. Here's a looping program for Matt's video that puts the number 3 into register 1, subtracts 1 by adding 255, and jumps back to the top. Once the register hits 0, this branch will take us to the halt line and stop the program. Putting this into Matt's assembler, we get the machine code, and using this Python script, we can turn that machine code into a schematic we can paste in the instruction memory. Now let's run this program and see what happens. So all we have to do is hit clock, and the thing is going to start. So we can see already our program counter is on line 1. We're going to see that instruction slowly light up over here. It is going to load immediate to our register. We're going to get a 3 in register 1. This turns on. We have a 3 in binary. We have 1, 1. We just have to wait a little bit. There we go. It gets unlocked, and then it gets locked again, and now we have a 3 in register 1. But it looks like it's working. The second bit is on, and everything else is gradually turning off. So our 3 is going to become a 2. So here is that repeater line once again, and once it hits the program counter, this should make it go from 4 to 2, so hopefully it works all correctly. And we have a jump. There we go. So then when the signal comes back around, basically subtract it from 2 to 1. Any second now. There we go. And locked again. So now we have a 1 stored in register 1. So now our bit in register 1 is going to become a 0. And then on the branch right after, it is going to actually jump to the halt line because it has met the condition of a 0. You can see that 0 is actually turned on, which means that this all the way here is turned on, which means the next instruction should be a jump. This should change to a 5, so it should be 1, 0, 1. There we go. That's 1, 0, 1. Our halt line should be activated. There we go. It's blinking a little bit. There we go. It's turned off. And now it has halted the program. So again, huge shout out to Matt Batwing's video on how to build a CPU and his whole series, because without him, this thing would not be possible whatsoever. And thank you again, boot.dev, for sponsoring this really silly video. You know, if you want to do something smarter than me, then again, go check the link in the description or pinned comment to check out their courses. And by the way, that 5-line program we just ran took, it took 21 minutes.